Right, continue our lesson on photoluminescence spectrometer, which I believe I have explained to you a little bit about the PL spectrometer in previous chapter in the SSC and also in QDSC. But now we have specific chapter for only the PL spectrometer. Now this will be the second last chapter, and next week we will cover the aquaponics system, which we integrate the aquarium and the hydroponic and also our photovoltaic technology. So these are the learning outcomes for the PL spectrometer. The first one, we need to understand the basic operation of PL. Any instrument, we should understand the basic operation from the source of the light and the application and all that. So number two, understand the standard operating procedure of PL, which I believe all of you has the experience to run your own PL spectrometer analysis. And number three is to understand the sample preparation procedure. Very simple topic. And these are the main components in the PL spectrometer, which the first one is the light source. It's an extension source to generate photoluminescence from the samples. So you need to understand, before understanding the PL spectrometer, we need to understand the absorption spectrometer, which we have covered in previous chapters. And number two, excitation monochromator. Similar to that of the absorption spectrometer, we need to have monochromator to filter out any unnecessary light source. So we need to be very specific, very discrete. We need to allow one wavelength at a time. So we need this filter or the monochromator. So the excitation monochromator is for the selection of specific monochromatic light with specific wavelength from the full spectrum of the excitation source. The light source gives you the whole spectrum from the, depends on the instrument. Some it allows to give you from ultraviolet to near infrared, depending on the specification of the PL spectrometer. Well, C, the sample chamber for optical components and sample holder. And we have another one is emission monochromator for the selection of specific monochromatic light from the full spectrum of the sample emission. So we have two monochromator. First monochromator for the light source, and second monochromator is for the light that is being emitted by the sample. So the sample might give you quite wide range of light, so we need to filter out any unnecessary light. Second last is the detector to detect the photon flux from the sample emission at the selected wavelength. And of course we need PC, which process the data and give you the graphs. So this is the light source, the compartment, which could be easily observed in our PL laboratory. You could come to the lab anytime you want. And the standard light source is 450 watt xenon arc lamp. It produces white light, and the spectral range is from 250 nanometer to 1000 nanometer of wavelength. So this light source will give us a little bit of ultraviolet to a little bit of near infrared light. From ultraviolet to visible to near infrared. It's from 250 to 1000 nanometer. This is an example of the spectrum of the light source. This is absorbance unit. This is the wavelength from 250, around 250 to 1000 is actually, and this one. This is different specification of the PL. 1000 gives us very specific, very distinct light source, and the rest of the spectrum, they only give us very small intensity, so we could neglect that one. Excitation and emission monochromator. A monochromator transmits a selectable narrow band of wavelengths of light from a wide range of wavelengths available at the input and output. So it is built in a box, which we could observe from the instrument. The box similar to like this. So this part of the instrument where we place the monochromator for the light source and also the emitted wavelength. So we have two types of monochromator, single grating and also double grating, but we won't cover that topic in this chapter, in this solar cell courses. So this one should be in the instrumentation or any related course. Sample chamber. place your sample and also your reference, but our system we don't need any reference, we just need to place our sample, whether it is thin film, powder or liquid. So if you carefully observe, you could see that the inside of this chamber we paint with black. Why? Because that black paint is actually to prevent from damage could be made by the solvent. It's a coating, special type of coating, which is could be considered as chemical resistant. And detector, we use photo multiplier detector. Standard operating procedure, I believe you already go through all the standard operating procedure in advanced material laboratory, so I don't need to tell much about the SOP. Demo video also, I have published this video in my YouTube channel. You could browse the video anytime you want. And this is the important thing. What else can we do using the PL spectrometer? The first one is we could calculate the energy loss in the fluorophore before electron injection begins. How? So we have this energy levels of our samples. This is the HOMO, this one is the LUMO. So whenever we give light source with specific wavelength, how much wavelength, how much energy do we need to excite an electron? It depends on our analysis using UVVs. So from the UVVs, based on the first excitonic peak, we could set the lambda that we want to use for the excitation of our sample. So if the light, the energy of light is sufficient enough for the electron to be excited, so the electron will be excited from the HOMO to LUMO, maybe LUMO 0 or LUMO 1 or LUMO 2, depending on the energy of the light. And basically, the electron, whenever it reaches at the higher energy state over here, they are not stable. They have a tendency to go down to the lower energy level. So the electron could be relaxed. The name of the mechanism is electron relaxation. The electron relaxes to lower energy level, maybe to LUMO 1 or also LUMO 0. So this one, during the relaxation, energy could be lost as heat. Then electron relaxes to LUMO 1 and electron relaxes to LUMO 0, and finally the electron could recombine with a hole in the HOMO. So during the recombination, this is radiative recombination, it produces light with lambda 2, and lambda 2 usually is longer than the lambda 1. Lambda 2 is bigger than lambda 1, which means that the energy emitted by the recombination is lower than the energy absorbed. This is energy conservation principle. Because some of the energy already released as heat, energy has been lost. That's why the energy of this emitted light is lower than the energy of the absorbed light. So what can we observe? So the light that is being absorbed by the sample could be studied using the absorption spectra, which the graph will give you. This is x-axis, the wavelength, y-axis is the absorbance. Why we need to study the absorbance? Because we want to study the light that is being absorbed by the material. Now the graph could be like this, a perfect graph, which the peak is distinct and we could observe, and we take note of the position of the graph of the peak, take note of the wavelength, and this light, the light that is being emitted, could be studied using the PL spectrometer. And PL spectrometer is known as emission spectra. And we plot the graph with the next y-axis, this is y2, PL intensity, the emitted wavelength, and the graph could be look like that, Gaussian type graph. And we take note of the position of the peak of the PL, and we got x2 and x1. This is not x. This is lambda sebenarnya. Lambda 1 and lambda 2. See, lambda 2 over here, lambda 1 is over here. And the difference in wavelength between the PL spectrometer graph and the peak in the absorption spectrometer graph is known as Stokes shift. Difference in wavelength. So from the Stokes shift, we could calculate energy loss easily. So energy loss due to electron relaxation is equals to energy of excitation minus energy of emission. Energy of light that is being used for the excitation and energy of the light that is being emitted by the sample. Simply calculate using Hc over lambda 1 minus Hc over lambda 2. Then we got the value. As easy as that. This is energy loss due to electron relaxation. Beside electron relaxation, what else? The source of energy loss that you could think of. Energy loss in our quantum dots, in our dye, could be due to the electron relaxation. Electron is being excited to the higher energy level, then it relaxes to the first LUMO and second LUMO, and energy loss is heat. What else source of energy loss that you could think of beside these two relaxation? Because energy loss is very crucial. In solar cell technology, we want to maintain the energy of this electron. If possible, we don't want this electron to lose any of its energy. Electron over here, we should pair with another semiconductor type, and that electron should be transferred to the neighboring semiconductor, so that the electron will flow without losing its energy. I mean, not without losing its energy, but we minimize the energy loss. So this relaxation is a waste. We don't want the energy of the electron to be lost as heat. We want to maintain the energy as maximum as possible and minimize the energy loss. So this one we cannot control because it is built in our material. The LUMO 0, LUMO 1, LUMO 2, they are built in. God has made it like that. We cannot control that. But what we could control is that the second component, which the electron will be injected, the LUMO of the second component should be the offset between the LUMO of this material and the neighboring LUMO should be minimized. That is one. How do we get rid of this relaxation? Number two, the second source of any energy loss in dye or any semiconductor is trap state. Let me draw it for you something. Back to the basic of solar cell technology. You know P-N junction, you still remember? To make things easy, we just use the valence band and conduction band to make things easy. And we have source of light, give us specific wavelength greater than the band gap. The electron will be excited here. Let's say. And we have second component, which is the neighboring semiconductor. Valence band, conduction band. The electron over here needs to be injected to the second component to initiate electron flow and create ISC, correct? This is the source of electron flow. When electron flow, electricity is generated. Agree? Betul? Still remember? Why are you guys so passive today? What happened? Okay, everybody stand up. Faizarin, help me out. Do a little bit of refreshment please, Faizarin.
Okay, macam doktor kata, kita perhatian sebab solar cell. Sebab apa kita sebut solar cell tu? kita sendiri semangat suara. Sebab kita kalau kita tak suara, kita diam ke, pasif kan Heidi? Betul tak?
Betul.
So apa kata kita sebut sama, okey? Perhatian.
Solar cell.
Tak semangat. Amir Lokman, tak dengar Amir. Arif, saya tak dengar suara kamu. Okey, sekali lagi. Perhatian.
Solar cell.
Guys, dia kuat lagi ni.
Dia gelak. Nak denda apa orang gelak ni?
Okey.
Dia kejap dia.
Come on. Semangat, energi sikit. Okey, perhatian.
Solar cell.
Tak fight suara aku. Perhatian.
Solar cell.
Okey, sikit lagi sikit. Perhatian.
Solar cell.
Allah, okey, slow balik. Orang kat sekolah rendah lagi kuat lagi suara korang tau. Okey, tak apa. Nice. Mari tepukan sikit.
The important thing in solar cell is that we need to make sure our excited state electron could be mobilized. The first principle of photovoltaic, we need to excite the electron, correct? Agree? Then the next step is that excited state electron need to be remain in excited state. The electron must not recombine with hole in the valence band. This electron must not recombine with hole in the valence band. When the electron has recombined with hole in the valence band, that electron is no longer mobilized. We need to maintain the electron at the unoccupied energy levels. At the excited state, whether this is at LUMO 0 or LUMO 1 or LUMO 2, we must maintain them in this region. So, that electron, we need to mobilize them. How to mobilize them? By pairing our first die, let's say this die or quantum dot, with the second semiconductor. And the semiconductor also has this conduction band and valence band. And the conduction band of the second semiconductor must be lower than the conduction band of the first component. Still remember that? And that electron must be injected to the LUMO or the conduction band of the second semiconductor. But before the injection could happen, if our LUMO is at this region, the electron which has been excited at the higher LUMO will relaxes to lower energy level, then they could be injected here starting from LUMO 0. And this is the source of energy waste, the wasted energy because of this the electron will relaxes, go down to the low energy level and release some of the energy as heat. We don't want that. So what can we do? Our LUMO must be a little bit higher than this one. I mean LUMO 0 still here, but LUMO 1 here, LUMO 2 here, such that this electron will be injected to LUMO 2 instead of injecting to LUMO 1 of the first component. Understand that? So this is source of energy loss. So what other sources? Trap states. Trap states appear here, in between the band gap. What are the sources of this trap state? Could be due to contamination. Structural defect and etc. Contamination. If our sample is contaminated with other material, that material could have conduction band and valence band as well. Maybe their conduction band is over here and their valence band over here, and they are creating this trap state. And this electron could also relaxes over here, relaxes here, and relaxes here before injected to the second component. Or structural defect. Structural defect is like this. Maybe during our synthesis, we could synthesis quantum dot with structure like this. Or with some error, our structure could be distorted. For example, if this is our cadmium selenide structure, it gives us this energy level, LUMO and HOMO. but with a slight twist of the structure, maybe distorted like this. See, distorted. It gives us different energy state. Maybe like this. The LUMO like this, and HOMOs like this, and give us this trap state. LUMO and HOMO. So also trap states. So contamination and structural defect give us this trap state and will give us energy loss before electron injection could happen. So how do we calculate the energy loss? Using the Stokes shift, just like what I have presented just now. Very easy to calculate. Just find the Stokes shift and convert them into the energy loss. Now we have covered this topic, the device structure of quantum dot solar cell and dye-sensitized solar cell. The differences we have covered that. The working principle also we have covered. And this one also we have covered, but I repeat just in case you forgot. So second type of analysis using PL spectrometer is electron injection efficiency from fluorophore to MOS. MOS is metal oxide semiconductor. Fatin akan buat, but you will focus on zinc oxide. Most of us we use titanium dioxide, but we don't want titanium dioxide because expensive and we need high temperature. So zinc oxide we could use low temperature. So Fatin, just imagine that this is your you will be playing around with the lead selenide as well, right? But your research will focus on MOS. Just imagine that this is your lead selenide. It is not, but just imagine this is cadmium selenide. So how do we do this analysis? We excite the electron in our quantum dots or dye. The electron will be excited, leaving hole in the HOMO. And this electron, it has nowhere to go. It will recombine with the hole and giving us radiative recombination and producing light. That light will be detected by the PL spectrometer and give us this graph. PL intensity, this is wavelength. So second procedure is that we need to fabricate the dye or the quantum dots or the semiconductor onto the metal oxide semiconductor. This is titanium dioxide. So your work will replace the titanium dioxide with zinc oxide. And this is the energy level alignment. So when we excite the electron in our dye or quantum dots, the electron will be excited, and the fate of this electron will have two consequences. The first one, 100% of this electron. I mean, why 100%? Because when we excite the electron in our quantum dots, not just one electron will be excited, many electrons will be excited, maybe 100 or more or less. So this electron, maybe 100% will recombine with the hole. So if 100% of the electron recombine with the hole, they are also producing the light. We could detect the light using the PL, and similar graph to that of this graph will be produced. That is the first consequence. Second consequence is that this electron will be injected to the conduction band of the metal oxide semiconductor, which this is the perfect condition for photovoltaic generation. We want this mechanism. So if this electron is injected to the conduction band of metal oxide semiconductor, this is non-radiative process. Non-radiative means it doesn't produce light, and if it doesn't produce light, the PL will detect no light. We got flat line. So if we compare with the bare quantum dots over there, the graph of the bare quantum dots and the graph with the graph of quantum dots and MOS conjugate, we could calculate the efficiency of electron injection. How? So if this is the case, this is 100% electron injection, 100% of this electron will be injected to the conduction band. This is what we want. We want 100%, or at least towards 100%. So how do we calculate? Using this equation. So let's say we have PL for bare dye alone without fabricating the die onto the titanium dioxide or metal oxide semiconductor. So let's say the intensity of PL of bare die is 80,000. We need to compare the graph with the PL of die and MOS conjugate. This is PL for die, this is PL for die which has been fabricated onto the TiO2 or zinc oxide. So we just need to compare the intensity. This is 80,000, this is 30,000. How do we calculate the electron injection efficiency? Electron injection efficiency could be calculated using this equation. PL of bare die, this one 80,000, minus of PL die MOS, this one 30,000, divided by PL of bare die, which is 80,000. 80,000 minus 30,000 divided by 80,000 times 100, we got 62.5% of electron injection efficiency. So if we refer back to this one, 62% of electron managed to be injected. The remaining 30%, over 30%, they will be recombined with coal. Understand to calculate? Very easy calculations. And no, you don't need to do this one because most of you has already done this during the advanced material lab. Any question before I move on to the next chapter? How many analyses that we could do in PL using PL spectrometer? 2. The first one is energy loss. Second, electron injection efficiency.